Hi, everyone, and thank you for joining us today for this webinar. Jason Allen here, the Concrete Pipe Guy. I'm the Technical Resource Engineer for Oldcastle Infrastructure, and I will be presenting today's webinar. Our topic is rigid versus flexible pipe installation, a side-by-side comparison. So before we begin, I want to tell you a little bit about myself. I currently live in Utah. I'm a proud University of Utah graduate with bachelor's and master's degrees in civil engineering. I've been in the engineering industry for over 20 years now, and when I was 18 years old, I started working as a surveyor and then transitioned into drafting and design, mostly in land development. I then worked in the public sector as a county engineer and public works director, and I've also done consulting engineering work in roadway and drainage design for the Department of Transportation and for large municipal projects. Now I'm a technical resource engineer for Oldcastle Infrastructure. So some of you may not be familiar with Oldcastle and what we do, so I'll quickly share some of the solutions that we can help provide. Now, I currently live in Utah. I spend a majority of my time working with engineers, contractors, inspectors in the Mountain West area, and most people know us by our precast products, mainly reinforced concrete pipe, precast box culverts, manholes, catch basins. And while this has been our main focus for many years, we have added some really cool new product lines to help us meet your needs. So Oldcastle recently acquired Torrent Resources, a company out of California that's the industry leader in drywall manufacturing and installation. We also expanded our stormwater solutions recently to include Storm Capture, which is a total stormwater management system that uses precast sections for underground detention storage. And this system uses the strength of reinforced concrete to provide more volume for your storage, which drastically reduces the footprint compared to other underground detention systems. We also have multiple stormwater treatment system options like sediment traps or hydrodynamic separators that could fit your specific needs and your stormwater treatment requirements. And our newest addition in the Utah market is gasketed box culvert. So instead of the typical soil type mastic joints, we now have the ability to manufacture gasketed box culverts to provide a watertight joint without any additional joint treatment, which saves time and money on installation. Now, in my last webinar, I showed a side-by-side comparison for rigid versus flexible pipe as it pertains to design. Now, if you haven't had a chance to watch that webinar, I suggest you do so, as this webinar will be building on the concepts that we discussed previously. So today I'm going to show you a side-by-side comparison between rigid and flexible pipe, but I'm going to focus on the installation of the pipe. Now, similar to our previous webinar, we will focus on the two national ASTM specifications to highlight the differences between the two types of pipe. This is valuable information not only for the project engineer, but also for contractors, installers, and inspectors as well. So just a quick review from our last webinar. Buried pipe has to perform two critical functions. Okay? It has to act as a conduit, and it has to act as a structure to hold the loads above it. So the two different types of pipe we're going to be talking about today are concrete pipe, which we know from last webinar is an engineered product, and it is plant tested. We have a structural engineer in the plant. We have a quality control guy who is doing all of our testing, making sure that it meets the loading requirements that we need it to for concrete pipe, because it is engineered and plant tested. Now, flexible pipe, and what we'll be focusing on today is thermodynamic plastic pipe. That is an engineered installation, and it should be field tested. At least we hope it is. And so we'll talk about the difference between plant tested and field tested, an engineered product and an engineered installation today. So if you remember last time we talked about a hypothetical solution, I'm gonna call back on that again. The construction drawings for a project called for 48-inch reinforced concrete pipe. The contractor wants to use 48-inch HDPE because his brother-in-law is the plastic pipe sales rep. Okay, the contractor plans to install the HDPE pipe just like he would reinforced concrete pipe. So you're the project engineer. Do you approve the change as is? So as I mentioned before, we looked at this from a design standpoint last webinar, but this one we're going to look at it from an installation standpoint and what the responsibility is of the engineer in installation as well. So for concrete pipe, we are going to be looking again at ASTM C1479, the standard practice for installation of precast concrete sewer, storm drain, and culvert pipe using standard installation methods. And for flexible pipe, we'll be looking at ASTM D2321, standard practice for underground installation of thermoplastic pipes for sewers and other gravity flow applications. All right, so let's talk about the pipe and the cross-sectional area of the pipe and what we're looking at here. So with concrete pipe, We've got a similar situation between the two, but if you notice the gray box down there, that's going to be our foundation, right? We want to make sure that our foundation is solid and strong so that we could build on top of that. Just above that, the area between where it says haunch, that orange area, that little space there, that is our bedding. So it's typically about 4 inches of bedding that we have there between the foundation and the pipe itself when we actually bed it. You've also got the haunch area there. And you notice we've got our cover, our pipe inside diameter there. So with flexible pipe, it's very similar, right? We've got all the same components here, but this is where it gets a little bit different. So we know that concrete pipe is acting as a conduit. We know that flexible pipe is acting as a conduit. However, concrete pipe itself is also the structure, right? Because it is a plant-tested structural element that is designed to withstand the loads. So when we look at the pipe itself in the haunch area, the bedding, the foundation, right, that we know that that's the structure there. However, with flexible pipe, we have to, as we'd mentioned last week or last webinar, that our biggest concern is that as that pipe is loaded on the top, it's going to want to squash or deflect, right? So the sides of that are going to want to expand outward. So in order to prevent that from happening, we need to compact really strong material on the side of that pipe to keep it in place and keep it tight there. So if the pipe itself is the structure on concrete pipe, for flexible pipe, the entire area around it, the soil columns on the side of the pipe, the bedding underneath it, the fill over the top to bridge that becomes the structure. So if you notice from these two diagrams here, it's a dramatically different structural element here where one, the pipe is the conduit in the structure, and with flexible pipe, the pipe itself is the conduit, but you are required to build the structure around it. So when you ask on concrete pipe installation, is it important? Yes, it is very important, right? Installation is important for concrete pipe. But if you ask the question for flexible pipe, is it important? No, it's not important. It is critical. It's critical that it's built correctly, because if you're not building that structure, then we're not sure that that pipe's going to be able to withstand those loads above it. And that is a very big problem. All right, so for concrete pipe, as we mentioned before, in the specifications that we're looking at, the engineer is on the plans going to say, manufacture this pipe per ASTM C76 and install the pipe per ASTM C1479. Manufacturer says, okay, C76, that's how we build our pipe. We're good to go. We'll build it. Installer said, great, ASTM C1479, that's how we're going to install it. We'll install it that way. Perfect. And we're done, right? Now, with flexible pipe, it gets a little bit different because as engineers, we like to say as per manufacturer's recommendations. So we try to alleviate any reference back to us. So we say, okay, we're good. We're putting all of the onus and responsibility on the manufacturer. So when we do that, the manufacturer on all of their references and all of their literature, they say, as per ASTM D2321, which is the installation spec. So they're referencing a specification that still all is fine. It comes back when we look at ASTM D2321. ASTM D2321 references the engineer and their responsibility on what they need to include in the plans and the specifications to ensure that this is built correctly. It references their responsibility 29 times. So it goes right back to the engineer. And so as the engineer says, as per manufacturer's recommendations, it comes right back to them on what their responsibilities are because of this ASTM D2321 spec. So we probably ought to look at these two specs and see what they say. So on the left-hand side of the screen, we're going to be looking at concrete pipe and ASTM 1479. And on the right-hand side, we're going to compare the different sections of things on this installation spec between concrete pipe and flexible pipe. So we'll be going through this relatively quickly. But, if you have any questions, I'll put my contact information up at the end of this webinar, and you're more than welcome to reach out to me if you want any more information on any specifics here. So when we look at concrete pipe, this talks about the scope of what it covers the installation of precast concrete pipe intended to be used for the conveyance of sewage, industrial waste, and stormwater for the construction of culverts. Okay. Now with flexible pipe, I've highlighted a few things so that we can look at them as we go through. This is from scope section 1.1. This practice provides recommendations, right? So it doesn't cover the installation. It just provides recommendations for the installation of buried thermoplastic pipe used in sewers and other gravity flow applications. If we move on to section 1.2, it says the scope of this practice necessarily excludes product performance criteria such as minimum pipe stiffness, maximum service deflection, or long-term strength. Thus, it is incumbent upon the product manufacturer, specifier, or project engineer to verify and assure that the pipe specified for an intended application, when installed according to procedures outlined in this practice, will provide a long-term satisfactory performance according to criteria established for that application. So here it is right off the bat, the very first section here. It's talking about the responsibility of the engineer to verify all of these things and to go through the proper calculations as we went over last webinar to make sure that this is meeting the long-term strength requirements. It will have satisfactory performance, etc. Okay. There is also a commentary on factors that's important in achieving a satisfactory installation, and that is included in this spec in Appendix X1. So that's where it talks about what you need to do to ensure that the installation is satisfactory. So as we move on to section 2, we talk about the reference documents for concrete pipe. We have 7 total ASTM standards referenced. In D2321, there are 23 total ASTM standards that are referenced. There is also 4 AASHTO standards for soil classification, density, and moisture. There's only 1 standard for AASHTO referenced in 2321, and that is for soil classification. And then in 2.3 of section 14.7 or specification 1479, there is the ASCE standard, ASCE 15, the standard practice for direct design of buried precast reinforced concrete pipe using standard installations. That is also referenced in that specification. So when we move on to section 3, we'll look at terminology here. It talks about the different definitions and where to find those. So as I mentioned before, in terminology, they reference C822 for the terminology as it relates to the concrete pipe. There's also D2487 and D2488 for soil classifications, and then ASCE 15 for the structural design of the pipe. So that's what the terminology is there. When we look at another one here, we've got the figure 1 that illustrates definitions and limits of the terms, talks about foundation, subgrade bedding, all of the things that are in the pipe, the cross section that we look at in there. So with flexible pipe, we also have terminology here. They've got the engineer, what it talks about, the foundation, bedding, haunching. It also has that modulus of soil reaction that we discussed in our previous webinar. So when we look at these two, these are the kind of the critical elements here. Section 3.3.3, the engineer. The engineer, and this is what's referenced 29 times, so we want to make sure that we know what the definition is. The engineer in responsible charge of the work or his duly recognized or authorized representative. And then section 3.3.6, the modulus of soil reaction, E prime. If you remember, this is the element of that equation, the modified Iowa formula that accounts for a lot of the structural capacity of that pipe to withstand deflection. If you remember, this is a really important critical number that we were kind of pulling out, and we said, well, where do we get it? I wasn't exactly sure where you get it. This defines what that is, and it says it's an empirical value used in the Iowa deflection formula that defines the stiffness of the soil embedment around a buried pipe. So again, it's only talking about the stiffness of the soil, but we have to make sure that we are building that soil to be as stiff as the engineer tells us to make sure that we're achieving that E prime number that helps us keep it within the allowable deflection limits that we talked about in the previous webinar, which for most municipalities in most states is 5% or less deflection in a flexible pipe. Okay, there's also obviously the 2 sections, 3.4 and 3.3.4 here in concrete and flexible. They both talk about the different definitions of foundation bedding, and there's a different figure for both of those that we look at. So let's go ahead and take a look at that figure here. So this is for concrete pipe. If you notice here, it's got a note that says clearance between pipe and trench wall shall be adequate to enable specified compaction, but not less than DO, or the outside diameter, divided by 6. So that is the limits that we've got there. So for flexible pipe, it also has a little note here that says, excavated trench width, right? We want to make sure that we're doing it wide enough to ensure that we've got compaction on either side of that. And we'll be talking about what that means in a moment. So the foundation, we want to ensure that we've got good foundation on both of those. If required, in some cases in flexible pipe, we'll need to over excavate and build a bigger foundation there so that we can make sure that it's not going to sink and move on us and that it's sound and stable. We also have here the outer bedding material and the compaction on each side to make sure that it's compacted well on the side there under the haunch. But also I wanted to point out here that the recommendation for concrete pipe is to leave the middle bedding loosely placed and uncompacted unless you're using type 4 then everything's left loosely placed and uncompacted. But if you're doing any type of installation 1, 2, or 3, then you want to leave that middle third uncompacted and loosely placed so that pipe can bed into it and nestle into that, so that we're distributing that load along the bottom of that pipe, not just at a single point load along it. So it's actually stretching it and distributing that over a larger area so that it helps that pipe perform correctly. So on this side over here, you notice we've got the yellow area here as well. That's the bedding on the flexible pipe. So we've got bedding underneath that and the recommendation that we have there. On the concrete pipe, we want to look at the haunch, right? The haunch is any area under the spring line. So that would be between your bedding and your spring line. So we want to make sure we're getting good material down there, that we've got some good compaction in there to make sure that that material fills in underneath and supports the pipe as it's supposed to. All right. And then there's information on table 2 with the haunch there. For this on flexible pipe, you've also got haunching directly under the pipe, but not necessarily the trench, the trench walls itself around the pipe, those pillars, those columns we want to build, right? The haunching is just directly under the pipe. So we want to make sure that we're getting it under there as well. Now, when it comes to concrete pipe, at this point, we look at the bedding, the haunching, and then the pipe itself. We are now structurally complete. Once we have that installed up the spring line and that haunch installed up there to the spring line, we are structurally complete. We're done. We can now use our overfill or our backfill material that's called out in the trenches just to put right on top of that pipe. Our pipe zone is complete. We're structurally complete. Everything's done. That is how we design our pipe, and that's how it's supposed to be installed. Now, with flexible pipe, you notice that we've got the haunching, but we also need to build the pipe zone, right? That is that area, those columns on the side of that pipe that we need to compact strongly to make sure that that pipe does not move or deflect when we put load on top of it, right? We also have an initial backfill on top of it that, according to the spec, is a minimum of 6 inches, but most times we'll see that, depending on what the engineer says, that it may have to be a little bit more, but it cannot be less than 6 inches. We see typically, 12 inches or even more on larger diameter pipe. But when we look at that all together, the bedding, the haunching, the pipe zone, and the initial backfill, that is the pipe zone. That is the structural element of this pipe system that we're looking at. And we can then ask ourselves, well, is it structurally complete? We hope it is. We think it is. Generally, we would assume at this point that it is structurally complete. However, if we come back, we have to make sure that the engineer did the correct design, that they ensured that the modulus of soil reaction, that the way that we built it, the way that it's being installed, the way that it's being compacted on the sides there, it's the engineer's responsibility to ensure that it is structurally complete and that it has been compacted on that. So it's very important for the design engineer not only to go through and do the calculations, but to verify through inspection methods or through compaction tests or something, so that they can look and ensure that, yes, it does meet the design that they called for, and that modulus of soil reaction, that E prime number, that it meets the stiffness of the soil that we are providing. So is it structurally complete? Well, we hope so, but it is up to the engineer to verify that it is. Okay, so when we move on to section 4, the significance and use. For concrete pipe, this practice is useful as a reference by an owner and the owner's engineer in preparing project specifications. But for section 4 of flexible pipe, this practice is for use by designers and specifiers, installation contractors, regulatory agencies, owners, and inspection organizations who are involved in the construction of sewers and other gravity flow applications that utilize flexible thermoplastic pipe. Now, here's the precaution here. As with any standard practice, modifications may be required for specific job conditions or for special local or regional conditions. Okay, so we know that in this case, the modifications would be as the engineer goes through the calculations that we talked about in the previous webinar, as they go through there, if there are any things that need to be added or modified or changed, then they need to do that. That is why this specification is just a recommendation. It is not the end-all be-all for installation. It is a recommendation on what you should be doing when you install this, but it is incumbent and dependent upon the engineer to ensure that it is done correctly. All right. We talked about soils last time. Let's go back to the soils and talk about those again to make sure that we're understanding that. In sections 9, 11, and 12 on concrete pipe, it talks about the different types of installation. So here you have on the left-hand side of the screen your type 1, 2, 3, and 4. If you remember, the type 1 is your really stout, really strong installation, right? It's got your A1, A3 material compacted to a 95% compaction, right? It's a really good installation. You go all the way down to type 4. Type 4 is your really weak installation. It's your native materials. It's your no compaction in the backfill, no compaction on the haunching. It's just dumped in, and you just use kind of a lesser material. So in that case, for a type 1 installation, you can usually save your money on the class of pipe. So you can class down, as we talked in the previous webinar, that, you know, you may be able to use a smaller class of pipe, so we're not putting as much steel in that pipe because we have a really good installation. Whereas in a type 4, you might need to increase the class of pipe, use a little bit more steel in the pipe, because that structural element needs to be a little bit stronger inside the pipe itself to withstand those loads. So those are the differences, just high level. Obviously, go back and watch the previous webinar if you haven't had a chance, to make sure that you understand the different types of installation. And then along the top here, you've obviously got your bedding thickness, your haunch and outer bedding, and your lower side. If we use a typical type 3 installation, if you notice, this has your category 1, which is your really good material, your type A1, A3 materials, compacted to 85%. You've got your, this is on your haunch, outer bedding, and your lower side there. For category 2, which is maybe your lower grade material, slightly lower grade, that's a 90% compaction. And then category 3, that's your next lower grade of material, that's like your A3, A5, or A5, A7 material. So that's going to be your 95% compaction in your category 3. So those are the different things in type 3 installation that you can use all 3 types of category soils, so that you just compact them to a different amount there. Okay, now when we look at flexible pipe, when we're talking about materials, okay, this talks about the soil classifications grouped into soil classifications table 2 based on typical soil stiffness when compacted. Now, if we remember these ones here, okay, here's where we're at here looking at this. Your class 1 soil, that's your super soil, if you remember from our previous webinar. That's the one that there's no ASTO classification for a class 1. Okay, but if you move down to class 2, that's your A1, A3 soils. That corresponds to a category 1 in concrete. If you remember, we went into this pretty in depth last webinar, that a class 2 is equivalent to a category 1 concrete. Class 3 is equivalent to a category 2 in the concrete spec, and class 4 is the equivalent of your category 3. And then a class 5 is not for use as embedment. That's the same as a category 4 for concrete pipe, not suitable for embedment there. So these are your different classes of material, classes of soil here. Okay, if you move on to section 5.2, installation and use, it says table 3 provides recommendations on installation and use on soil classifications and the location that they can be used in the trench. Soil classes 1 to 4 should be used as recommended in this table. Soil class 5 not suitable, as we just mentioned. So if we blow this table up a little bit and we look at it, you've got your soils across the top there. Soil class, you've got your class 1, class 2, class 3, class 4. Now keep in mind, class 1 is that super soil, that structural soil that you have to order specifically. Nobody has that on file, right? That's just it's not a typical ASTO specified soil. So you're going to have to order that based on the design of that soil itself. So we kind of focus more on your class 2, class 3, class 4 soils, because those are the ones that are more readily available from your material provider. Okay, so if we look at the foundation here of what is suitable, and if you notice and you read through some of these recommendations on where they are suitable and acceptable, if you notice there at foundation for class 1, suitable as foundation and for replacing over excavated unstable trench bottom as restricted. So if you have to over X and put in new foundation, that's suitable. Class 2, suitable as foundation and for replacing over excavated unstable trench bottom as restricted above. Install and compact in 12-inch maximum layers. Also suitable for replacing over excavated trench bottom is restricted above for class 3. Install and compact in 6-inch lifts. And then class 4, suitable for replacing over excavated trench bottom for depths up to 12 inches as restricted above. Use only where uniform longitudinal support of the pipe can be maintained as approved by the project engineer, and compact in 6-inch lifts. Okay, so pipe embedment, this is the area around the pipe, okay, and where we can use that for the embedment here. This says class 1, suitable as restricted above, work material under pipe to provide uniform haunch support. Class 2, suitable as restricted above, work material under pipe to provide uniform haunch support. So we want to make sure we're getting under the haunches. Class 3, suitable as restricted above, difficult to place and compact in the haunch zone. Okay, so this one is one that you maybe don't want to use in that haunch area in class 3 and 4. Okay, also class 4, suitable as restricted above, difficult to place and compact in the haunch zone. Kind of interesting there. So when you look at, and I'll tell you why it's difficult to place, because this is where we come in here, right here. The recommended percent of compaction on these class 3 and class 4 are 90% and 95%, okay? The relative compactive effort required to achieve minimum percent compaction, if you notice in class 3, the effort required is high, and in class 4, the effort required is very high. And the compaction methods that it's recommending is impact compaction. So if you know anything about impact compaction, and as you go in here and you start trying to compact, especially under the haunches, and why it's so difficult to work under the haunches of these flexible materials here is, I'll show you why. If we look at these simple machines here that we've got, one of these references what it would be like if you were trying to compact under the haunch there. And we'll give you a second to think which one it would be: the lever, wheel, and axle pulling, clamp plane, wedge screw. If you guessed wedge, that is correct. So as you come in and you're compacting and putting the material under the haunch, and you're using your impact machine to compact that, as you're doing this compaction, what's it going to do to that pipe? It's going to want to lift it up. It's going to act as a wedge underneath that haunch. So the more we compact it, the more it's going to lift that pipe up, and it's going to act as a wedge to get it off of alignment. And you're going to have some pretty big problems there, which is why that class 2 soil, or the A1 or A3 soil, the class 2 soil is the best because it only requires 85% compaction under the haunches there. So you're going to want to use that better material, that more expensive and more reliable material of that A1, A3 ASTO classification soil, because you don't have to compact it as much, so it's going to be easier and it's not going to cause that wedge. Okay, so if we look at the bedding, we can look at the maximum aggregate size, 1 inch when the bedding thickness is less than 6 inches, and 1.5 inches where the bedding is 6 inches or greater. When we look at flexible pipes, similar here, maximum particle size for embedment is limited to material passing a 1.5 inch sieve. To enhance placement around small diameter pipe and to prevent damage to the pipe wall, a smaller maximum particle size may be required. So that's from Appendix X. As we mentioned, some of the things to keep in mind when you want a satisfactory installation. And then also, if we look down at X19, we'll go to that section here, maximum particle size. Limiting particle size to 3/4 inch or less enhances placement of embedment material for nominal pipe sizes 8 inches through 15 inches. So when you have that smaller size pipe, you want to make sure that you're using smaller particles, which makes sense, right? So let's look at our trench here. Now, as we go in, we had the note here on what the trench wall needed to be to make sure that we can get the installation there. We already talked about that one. And then the excavated trench width on the flexible pipe. So let's look at trench excavation here with flexible pipe. It says here, the space between the pipe and trench wall must be wider than the compaction equipment used in the pipe zone. That makes sense, right? If you got a 12-inch wide compactor, you can't have 10 inches in between the wall, right? You're not able to get it in there. So if you have 12 inches, you're going to need at least probably 14 to 16 inches on the outside, right? To be able to get that compaction. I mean, I guess you could do it with 12 inches, but you're getting pretty close to the wall there. You're going to want a little bit more. Minimum width shall not be less than the greater of either the pipe outside diameter plus 16 inches or the pipe outside diameter plus 1.2 times 1.25 plus 12 inches. So that's total width, if you remember here, right? So it's diameter plus 16 inches. So on that one, that's kind of interesting because when you look at the 16 inches, that's only 8 inches wide. So if your compactor is 6 inches, then yeah, the 8 inches should be enough. But if it's a little bit bigger, if you're compacting and your plate there is 12 inches, then you're going to need to go probably 14 inches on either side. So keep that in mind. Depending on what type of compaction material or compaction equipment you're using, you're going to need to make sure that they've got the correct trench width. All right. So if we look at the pipe, the different, based on that note on concrete pipe in 1479 and D2321, we can look at the size of the trenches of what they need to be for different pipe sizes here. Okay. So if you compare these tables to one another, right? One of them here on concrete pipe, you can get away with a slightly smaller trench on a lot of these sizes here than you would with flexible pipe. Now, flexible pipe has the 2 different methods of calculating what the trench width should be. So if you notice on one of them, on the 12-inch, the controlling factor is the outside diameter plus 16 inches. So, your outside diameter on a 12-inch pipe is 15 plus 16 is 31. However, outside diameter times 1.25 plus 12 inches is only 30 inches. So the controlling on that would be in 12 inches would be your 31 inches. So if you notice, some of these are quite a bit bigger there. Now, I like to look at the clear side, clear on each side. This is the clear distance on each side. So even let's look at concrete pipe. I mean, if you're doing a small installation of like a 15 inch or a 12 inch even, I mean, we're only talking 3 inches of clearance on either side. Is that enough on the side to get good compaction and good get that material down under the haunches? Remember, we wanted to get that material into the haunches there on the concrete pipe and up to spring line. It maybe isn't enough, all right, admittedly. So I always recommend that we look at these and say, okay, how much do you need to really do the compaction? That's what should be controlling. If you can get in there and compact it with 5 inches on either side in a 24-inch pipe, great. Then that's awesome. Do that. You know, obviously with concrete pipe, the compaction of those haunches and the compaction on the sides is not critical like it is in flexible pipe. It's important, yes, to get good material under the haunches, but it's not critical that it be compacted under there. So maybe if we're using a good material and an 85% compaction on that A1, A3 material, maybe we can just get that just by placing it in there and shoveling it in under the haunches. If we can do that in 3.5 or 4 inches or 5 inches of width there, then great. Get it done there. But with flexible pipe, we need to make sure that we have enough to compact, which is why we want a slightly larger and wider trench there. So if you notice on the other ones, like on a 24-inch pipe, you've got 5 inches on a concrete, but you need 9.5 inches on each side for flexible pipe. Is that enough to get the compaction done? Possibly, depending on what you're using. So that's what we gotta make sure that the contractor has something that he can meet these compaction numbers of either 85, 90, 95% compaction, depending on the material they're using, and make sure that they can get that with this amount of clearance on each side. Okay. So when we look at embedment, this is again from 2321. So I shifted flexible pipe over to the left-hand side here just so that I could show the example and the image on the right. But when we look at that X1-10, so this is again from that appendix that tells us what we need to do to make sure we have a satisfactory installation. In certain conditions, a minimum width of embedment material is required to ensure that adequate embedment stiffness is developed to support the pipe. These conditions arise where in situ lateral soil resistance is negligible, such as in very poor native soils or along highway embankments. Okay. Under these conditions, if the native soil is able to sustain a vertical cut, the minimum embedment width shall be 0.5 pipe diameters on either side of the pipe as shown in figure X1.1. So that's where we're at right there. If you notice over at on the right-hand side, that is figure X1.1. This is the minimum width that you need when we have an issue with the soil. So, all right, I want to make sure that we understand and we remember what we talked about in the previous webinar with embankment and versus trench construction. So embankment is where we put the pipe on the ground and we build the material up over the pipe. And then trench is obviously where the material is there. We dig a hole, we place the pipe inside the hole, and then we backfill it. So if we're using embankment, or if we have really poor native soil, so think of like a sandy soil or a really gravelly soil that when you dig into the trench, sometimes maybe we've been out on an installation and you dig into the trench and the side of that trench, the trench wall starts kind of collapsing and falling in on itself because maybe it's really sandy material or it's not well graded and it's just a really weird in situ soil there that just starts falling in on itself. In those cases, we want to widen that trench to make sure that we have good compaction and good soil on the side that we can build off of and build onto. Now, this only works in this one, mind you, if the in situ soils are in a state where it can sustain that lateral cut. So if it's not able to, then we've got a different one that we got to look at. But in this case, if we can, even if it's poor native soils in the trench, we want to make a wider trench so it would be half of the pipe diameter here. So you notice basically that 2D or twice the diameter of the pipe. Okay, so that is the outside diameter, the D there, you notice it goes to the outside of the diameter. So you need half of that diameter of the pipe on either side of the pipe. So you would need it to be two times that. So as we bring up a table here, if we look at it for a 12-inch pipe, we need it to be 30 inches wide. For a 24-inch pipe, it's going to need to be 56 inches wide. If you start getting up into the larger pipe diameters, like a 48-inch pipe, your pipe trench is going to need to be 108 inches wide. So pretty wide trenches there if you've got poor material there. Okay. Now for concrete, if we have embankment installation, we're able to get a little bit less on some of these, but we want to make sure that we've got our good side fill there, right? In our embankment, we want to make sure that we've got our lower side compacted as we go up and as we build this around the concrete pipe. So here's the embankment installation. We know that in order to build this correctly, we've got 3 times the outside diameter for those lower side for embankment, and how we need to do it there for installing on a concrete pipe. Now, if we're doing embankment installation or a trench with soil that is collapsing on itself that doesn't allow that open cut, okay, we also need to do pipe size with 3 times the outside diameter. Now, we don't see a whole lot of embankment installation in Utah, where I'm at, but other places across the country, you might see embankment installation, but where we don't see a whole lot of embankment installation. But what we do see, as far as with flexible pipe, the possibility of poor soils in our trench. So this is something to kind of keep in mind, that, these trenches could be really, really wide if we have poor soils, or if we are using embankment installation to make sure that we're building up around the pipe itself. So if we look at a trench installation for concrete pipe, we basically, the amount of soil that we need to become structurally complete, remember we talked about structural complete, and that it goes up from the bedding up to the spring line and then the pipe itself. So we would need about 9 cubic feet of soil per linear foot, right? So we're looking at 9 cubic feet per foot of soil. Okay, so that's just the cross section there as we look at it. Now, if we're using category 1, we need this compacted to 85% compaction. If we're using a category 2 soil, 90% compaction under there. Category 3, or the lower level soil, category 3 would be your 95% compaction. Remember, category 4 is not acceptable for this type of installation there. Okay. Now, with flexible pipe, in order to build this trench correctly with the pipe backfill, we need 20 cubic feet of soil per linear foot of trench. So that's 20 cubic feet of soil per linear foot of trench. Now, if we have poor soils and we need to look at widening that to twice the width of twice of the diameter of the pipe, now it goes up to 32.4 cubic feet per foot of soil. Now, keep in mind that if we were to use class 1 compacted, right, that's your super soil. But if we're using a category 1 in concrete pipe, it only needs to be installed to a 85% compaction in concrete. But for flexible pipe, it's the same soil, that A1, A3 ashdose soil. It needs to be compacted to 95% compaction. Okay, so not only if you're using the same material for rigid pipe, concrete pipe, we can use that material, but we don't need to compact it as much, which saves on installation time, it saves on labor, so it saves our money. So we're using less material, but we also don't need to work it as much as we need to with flexible pipe. So keep in mind that with concrete pipe, 9 cubic feet of soil, just to build the trench in optimal conditions, you're going to need 2.2 times as much material. In suboptimal conditions, right, you're going to need 3.6 times the amount of soil. Okay, 3.6 times as much soil, and it needs to be compacted to 95% compaction if you're using the same type of soil there for these trenches. So a lot more soil, a lot more material you're using, and you need to work it a little bit more. So it's going to take more material cost, and more labor cost to make sure that we're installing it and compacting it correctly. So for embankment, for a concrete pipe, we need 29.5 cubic feet of soil. Okay, if we're doing embankment or poor soil conditions. For embankment or poor soil conditions in flexible pipe, you're going to need 56.4 cubic feet per foot of soil. So that is almost double. So 1.9 times as much material, almost double. Again, if you go back to category 1, 2, or 3, you can use an embankment installation for concrete pipe. For flexible pipe, you're only allowed to use class 1 or class 2. For class 2, you need to compact it to 95%. So it's twice as much material compacted to a lot more compaction than we need in concrete pipe. So keep that in mind. All right. So when we look at trench excavation, this is an interesting one. Movable trench wall supports, or as we see these movable trench wall supports, we've seen these on all of our projects, right? As we start moving those, this is a concern when you start talking about this, because it says right here, do not disturb the installed pipe and its embedment when using movable trench boxes and shields. So if you've got a trench box down in that trench, right, it does not want you to disturb the installed pipe. So think about that for just a minute on what that looks like. How do you install the pipe and meet OSHA safety requirements with a trench box, but not disturb the pipe itself? Okay, so movable supports should not be used below the top of the pipe zone unless approved methods are used for maintaining the integrity of the embedment material. So, okay, so think about that as well. Movable supports should not be used below the top of the pipe zone unless approved methods are used. Okay, interesting. Okay, so let's look at this. This is a sub-trench installation from one of the pipe manufacturer's technical notes. So you look at this and how they show that it should be used. But to me, that looks like it's violating the recommendation there that says movable supports should not be used below the top of the pipe zone. If you remember, the top of the pipe zone is the top of the pipe plus either 6 or 12 inches there. But even if we brought it up to the top of the pipe, how do we use a sub-trench installation, and how do we use that where it looks like it's still below the top of the pipe, right? Because so before moving supports, it says place and compact embedment to sufficient depths to ensure protection of the pipe. As supports are moved, finish placing and compacting the embedment. So in order to meet the trench width requirements and the trench safety requirements, we have to have this trench box in there, but we've got it in a sub-trench sitting on the shelves there. It can't be below the top of the pipe or the pipe zone. So when we look at the pipe zone, that's what the pipe zone is there. If you try to reconcile those two on how you can install this correctly with a trench box, it becomes really difficult to try to make heads or tails of how we're going to install that with a trench box. And as we move that trench box, how we're going to continue to compact. So the sub-trench is a fine idea if the pipe is small and we can get it in there and we can install around it. But what if we're dealing with a 36-inch pipe or a 24-inch pipe even? I mean, if we have that and we can dig our sub-trench down 2 feet, we're not able to get our bedding or anything up above the top of the pipe. So it really becomes a curious problem when we start looking at deep trench installation here. If we've got anything over basically 4 feet of a trench and we need to use a trench box, this becomes somewhat of a conundrum. And it makes really difficult for installation to do it the way that the specs call out. And, you know, the engineer is going to be responsible for this. So they've got to certify that it was built correctly. So if we look at these two and try to reconcile those two, and you go back to this note, before moving supports, place and compact embedment to sufficient depths to ensure protection of the pipe. As supports are moved, finish placing and compacting embedment should not be used below the top of pipe zone unless approved methods for maintaining integrity of embedment material. This becomes a problem if you're the engineer that has to sign off on this and ensure that it was installed correctly. So keep that in mind. All right, so when we get into the foundation here, 8.1 for C1479, foundation shall be moderately firm to hard in situ soil, stabilized soil, or compacted fill material. For the trench bottom, for D2321, it says install foundation and bedding as required by the engineer. There it is again, engineer's requirement, according to conditions in the trench bottom. All right. When we look at C1479 for concrete pipe, when unsuitable or unstable material is encountered, the foundation shall be stabilized. Pretty simple. Okay. However, for flexible pipe, when there's unstable trench bottom, where the trench bottom is unstable or shows a quick tendency, excavate to a depth as required by the engineer and replace with a foundation of class 1 or class 2 material. So again, the responsibility is on the engineer to determine the depth that it needs to be put in there. There's really no recommendations here on how deep an unsuitable trench bottom should be. But that is up to the engineer to run the calculations and determine what that depth is, and then what type of material it needs to use. You can use class 1 or class 2, but again, it is up to the engineer to determine what that should be. Okay. So when we look at concrete pipe and our types of installation and our different types of material, what we can use for the haunch, the lower side, we've gone through these so much on what can be used on these different types of materials or types of installation. So we won't rehash that. But for flexible pipe, when we look at the percent compaction of embedment, the soil class and the required percent compaction of the embedment should be established by the engineer. Again, engineer's responsibility there, based on an evaluation of specific project conditions. So we need to look at those conditions of what we have in the field, what the soil looks like, what the in situ soil is, and determine that percent of compaction of the embedment there and what type of material we're using, right? Are we using a class 1? Are we using a class 2, class 3? What are we using in these to ensure that we've got the correct type of embedment here, right? Now, the information in Table 3 will provide satisfactory embedment stiffness and is based on achieving an average modulus of soil reaction, E prime of 1,000 PSI, or an appropriate equivalent constrained modulus. So this is telling us that if we follow the table that's put in the spec, this will achieve an average modulus of soil reaction, E prime of 1,000 PSI. So it will achieve an average, but again, it's on the engineer. It's the engineer's responsibility to make sure that it is being done correctly and that it is installed correctly and that it meets that E prime number correctly. And if it doesn't, then who's liable? Who's responsible? So if it's an average of 1,000 PSI, but we designed it to be 1,000 PSI and it falls below that because we're just averaging it, does that cause a problem and cause our pipe to deflect more than we need it to, or more than is allowed? It's possible, I guess. So that's concerning. So keep that in mind there. As we look at section X1-6-2, embedment compaction, it says embedment compaction requirements should be determined by the engineer based on deflection limits established for the pipe stiffness, and installation quality control, as well as the characteristics of the in situ soil and compactability characteristics of the embedment materials used. So again, on the engineer to determine the deflection limits, make sure that the pipe and the pipe stiffness and installation and everything is done correctly to make sure that it does meet these requirements, that E prime number, right? And then if you go down to the bottom of that as well, for particular installations, the project engineer should verify that the percent compaction specified meets performance requirements. So again, there's that pesky term there of what the engineer's requirements are or responsibilities are, I should say, to make sure that we're meeting the performance requirements. So here's a picture. I just wanted to show you what it looks like if we're installing on the side of that pipe. We want to make sure that we're installing on both sides. We're compacting on one side and then the other. We don't want to get too high on one side because then we've got other issues there as we compact it. But this is a good picture of how much space you need on the side of that pipe to make sure that we are meeting adequate compaction. Okay, so for concrete pipe, if you remember, if we're going to talk about cover here, cover requirements, we went to the fill height tables and we looked at what class of pipe we need, I guess I should say, for the different classes of pipe for different types of bedding. This is the type 3 installation. So for that, if we go with a 1 foot of minimum cover, we need a class 4. We can look at some of the others there, the other sizes for a class or a 12-inch, a 15-inch, 18-inch, we'll need a class 4. For 21 and 24, we can do a class 3 pipe, and all the rest, if we have just 1 feet of cover on it, we can go class 3 or less. So we should be fine there. So that's how we figure out minimum cover requirements for concrete pipe and how the engineer verifies that, but it's a little bit different on flexible pipe. So for minimum cover, it says the minimum depth of cover should be established, again, you guessed it, by the engineer, based on an evaluation of specific project conditions. In the absence of an engineering evaluation, the following minimum cover requirements should be used. For embedment materials installed in accordance with Table 3, provide cover of at least 24 inches or 1 pipe diameter, whichever is larger for class 1 embedment, and a cover of at least 36 inches or 1 pipe diameter, whichever is larger for class 2, 3, and 4 embedment, before allowing vehicles or construction equipment to traffic the trench surface, and at least 48 inches of cover before using a hydro hammer for compaction. So that's the recommendations that flexible pipe gives if the engineer is not going to do a minimum cover evaluation. This is what they recommend: 24 inches for a class 1 embedment, 36 inches for class 2, 3, and 4, and then make sure there's at least 48 inches before you use hydro hammer for compaction. So here's a table that just shows what the recommendations are for all the different types or the different sizes of pipe, what the recommendations are for your minimum cover. So a lot of places could say, oh, I have a really shallow bury installation here, and I've got an 18-inch pipe and I need to put, I only have 12 inches of cover between my top of asphalt to the top of pipe. Can I make that work? And in this case, it could work for concrete pipe. We just increase the class. But for flexible pipe, it looks like unless it's 24 inches or less, you're probably not going to be able to do anything with 12 to 18 inches of cover. You're going to need to look at the 24 inches of cover there. So again, if we go back to the technical note, this is a technical note that talks about the possibility of flotation. The lightweight of high-density polyethylene and polypropylene make it desirable because of the ease of handling and installation. But this same benefit also makes these thermoplastic pipes prone to flotation. So as we look here, this is table 2, a minimum recommended cover to prevent flotation of thermoplastic pipe. So this is also from that same technical note there that you can research on your own if you want, but it tells you about the minimum cover required to keep the pipe from floating based on the size of diameter there, your nominal diameter, on how much material is needed to ensure that it doesn't float. So for structural purposes, a minimum cover of 12 inches shall apply for 4 to 48 inches of pipe and 24 inches for 60 inches of pipe, which again, for structural purposes, that kind of doesn't really coincide with D2321 and what their recommendations are on how much soil you should have on top of it. But this is just in the case of flotation. So obviously the lightweight pipe, if you don't have enough material on top of it, the groundwater pushing up that hydrostatic force can push that pipe up and lift it so that it actually floats. And you can notice there sometimes it will lift up so much that it brings up the entire column of material on top of it with it, if you have a lot of groundwater there and a lot of pressure pushing up on it. So this is a pipe that floated up out of the ground there and lifted the soil column on top of it. So some options you have are tie downs, using tie downs there to tie the pipe down and anchor it into the foundation so that it doesn't float on you, especially if you're using like a flowable fill, like a concrete mixture to backfill the pipe there, some type of flowable fill that really has a tendency to float a pipe. So you want to make sure that it's anchored in correctly so that as you backfill that and you're coming up with that flowable fill, it's not lifting that pipe up as it goes, because the density of flexible pipe is less than the density of that material that you're putting in there. So keep that in mind. Okay. So safety requirements for construction shall be in accordance with applicable federal, state, and local regulations for concrete pipe. Open ends of installed pipe shall be covered during overnight and longer periods of suspended work to prevent access by animals, personnel, accumulation of soil and debris, etc. Covers shall not be braced or fastened to prevent movement. It is not required that these covers be watertight. So that's for concrete pipe. You don't need watertight covers for safety. Note 3, if the pipe is plugged watertight, when empty, the possibility of pipe flotation should be investigated, and if necessary, appropriate measures shall be taken to prevent flotation. So it is possible that if you were to plug those and keep it filled, it is possible that if there are watertight connections there at the end as you plug the concrete pipe, it's possible that it could float. There was a study put out by the American Concrete Pipe Association of flotation and a buoyancy comparison, and this talks about why flexible pipe floats when precast concrete pipe won't. It talks about, in most cases, concrete pipe, because of its density, will not float. Conversely, flexible pipe, which has been touted as lightweight and easy to install, is extremely susceptible to flotation. Average density of concrete pipe is 150 pounds per cubic foot, which is almost 2.5 times that of water. However, the density of corrugated polyethylene pipe with an interior liner is as much as 6% less than water. So it will float in water if water comes up on it. So keep that in mind, that it could have some type of flotation there, where concrete is 2.5 times heavier than water. Flexible pipe is lighter than water. Okay. For field monitoring here for installation, it says safety should be monitored by the engineer at a frequency appropriate to project requirements. So again, the engineer is responsible for the project safety and making sure that it doesn't float and that there aren't issues there out in the field. So concrete appurtenances, so like manholes, they'll be installed in a manner that will minimize differential settlement between pipe and manhole. That's always a problem, is getting that compaction around the manholes and making sure that our pipe and our manhole don't settle. Precast concrete fittings such as T's, Y's shall be bedded, installed, and overfilled with the same material and in the same manner as the remainder of the pipeline to reduce the possibility of differential settlement between pipe and fitting. So that's, pouring a concrete collar around it to ensure that it's connected so that it doesn't move and go anywhere. Now with flexible pipe, when we have manhole connections, this recommends, ASTM D2321 recommends that we use flexible water stops, resilient connectors, or other flexible systems approved, again, by the engineer to make watertight connections to manholes and other structures. So we're looking at like a boot, for instance. Okay, this is a picture that I love. I'm just so proud of this contractor. Look how happy he looks. He's putting bricks around that flexible pipe, and he's grouting it in. I mean, he's just so darn proud of himself. He's so happy to be out there doing this work. Maybe what he's laughing about is he knows that if that pipe were to deflect, if it gets loaded, then that pipe's just going to crack that grout. You're going to have issues with the water leaking there. That's why they want you to use this flexible connector, like a boot, a rubber boot or something, because as that pipe, we know that pipe's going to deflect even a little bit, right? Up to 5% is acceptable. So if that pipe deflects 5%, if it's a rigid grout like we use in concrete pipe, that's fine because the pipe isn't going to deflect, right? But if it's a rigid grout like that and that pipe deflects, it's going to crack the grout and it's going to fall out. It's going to wash in. It's going to have groundwater and other material enter and debris enter our manhole, and it's going to be a problem. But that's why they want flexible pipe to use these flexible boots on these manholes as they connect them, because it will give and it'll ebb and flow a little bit with the deflection of the pipe. So it's not going to be a problem when it deflects. It's not going to crack the grout and it's not going to crack that rubber. Everything's going to work together, right? Here's another picture that I love with where they grouted in a flexible pipe. That is unacceptable. Kind of a cool brick structure though that they built there to tie that into. But again, the grouted pipe there for the flexible pipe is not going to work. It's not going to give with it. So it should be a rubber connection or some type of flexible connection, like a flexible boot there. Okay, so when you look at manhole connections here, it always recommends there that you've got your flexible boot, your watertight connector that's flexible so that it can give and move a little bit there. So just wanted to point that out, that just installing the pipeline isn't always the only thing we got to focus on as engineers. We have to also look at how we're connecting these to our manholes and our catch basins. All right. So with field monitoring, again, compliance with contract documents with respect to pipe installation, it should be monitored by the engineer to make sure that it meets the project requirements there, make sure that it's connecting correctly to that. All of this falls on the engineer. So when we look at this trench here without trench boxes, it's pretty wide. It's pretty high there. Are they doing this? Does that meet safety OSHA requirements and safety requirements? Hard to say. It depends on how that slope's laid back, but it's going to be really hard to meet that. So that's, again, the responsibility of the engineer to make sure that that's being done correctly, right? Is that pipe, that end there, is that being installed correctly with the trench boxes? Is it covered up correctly to ensure that something doesn't get in there? Is it anchored correctly? It looks like you got a trench box there on the side and then nothing opening up there. So there's obviously shovels down there, so someone's been down there. So these are issues that we need to take into account when we're engineers, and looking at all of these different things. You've got a lot of material being pushed on the side there, that flexible pipe that, it might, as that material is dumped there and it moves, is it going to lift that pipe up? Is it going to shift it? Is it going to move it? These are all things that we need to look at when we deal with, embedment, backfill materials, the foundation, making sure that it's correct, right? As we look at that trench materials in the foundation there. What about joints? Are the joints correct? That looks like a pretty interesting and unique way to grout in a joint there. Does that meet the specs? It sure doesn't look like it. When we talk about safety, is that a safe use of that trench box? Hard to say there. Doesn't look like it to me, but that's up to you as the engineer to determine. So as we get through here and we look at our pipe, we've done our pipeline, we come in, we do our end treatment, and as we get through this, oh, hooray, installation was successful. The pipeline is complete. Or is it? Was the installation successful? I don't know. What's the best way to find out and know? Well, the best way to know if a pipe was installed correctly was field inspection of pipes. So when we look at concrete pipe, there's a recommendation for inspection that says the owner is advised to provide for or require adequate inspection of the pipe installation at the construction site. With flexible pipe, they recommend deflection testing. To ensure specified deflection limits are not exceeded, the engineer may require deflection testing of the pipe using specified measuring devices. To allow for stabilization of the pipe soil system, the deflection tests should be performed at least 30 days after installation. However, as a quality control measure, periodic checks of deflection may be made during installation. Now, think for 1 second, as you think about 30 days of installation, 30 days after installation, what happens typically within 30 days of installing a pipe? Well, typically your storm drain pipe might be one of the last things to install. So after you put your storm drain pipe in, you've got it in the ground. The next 30 days, you're going to come in and put your trench. You're going to fill your trench up. You're going to put your granular barrow in, your untreated base course. You maybe put your asphalt surface on the top there. You'd put your curb and gutter in. You know, there's a lot of things that can happen within 30 days. So if you're not able, if you're allowing this to stabilize and you're waiting 30 days and you find out 30 days later after you do your deflection test that it doesn't meet the deflection requirements, now all of a sudden you got to go in and rip up that section of pipe to replace it. What does that do to everything up above it? It's quite an issue. So in section X1.13.1, it says optional devices for deflection testing include electronic deflectometers, calibrated television or video cameras, or a properly sized go, no-go mandrel. Okay, so when we test concrete pipe, we verify the strength before the shipment, right? We put it on our 3-load bearing test, and we run a test on it there, and we make sure that it meets our strength requirements before we even ship the pipe. Okay, deflection testing is not relevant because concrete pipes don't deflect, right? They may crack if you load it too much, but they're not going to deflect. Okay, now with flexible pipe, this is a mandrel or a go no go device with 9 fins coming off of it. There, it's sized to meet your deflection requirements, whether that's 5% or whatever it is. In most places, it's going to be 5% deflection is allowable. So it's set to 5% deflection of the internal diameter, and then you pull it through and it gets stuck if the deflection is exceeded. So it looks something like this. You've got your roller guides on there. You've got one person pulling it by hand. They recommend that you do it by hand. Someone asked if they could just tie it to the winch on their truck and pull it. And I said, well, you won't really know if it gets stuck, but you'll have a nice ripped 9-fin hole in the pipe where it didn't fit through there. So you pull it through on these roller guides here. It's set to that diameter. You pull it through, and if it gets stuck, we know that it has exceeded that amount of deflection there. This is another report put out by the American Concrete Pipe Association, Post-Installation Inspection Basics. And it says the post-installation inspection provides the proof of proper installation and structural integrity to the owner prior to project closeout or final acceptance. So if you're the project engineer and it's your responsibility to ensure that this was installed correctly, one of the best ways to do that is to require post-installation inspection and what you should be looking at there. So in this report, in this recommendation, it says 100% of all reinforced concrete pipe installations should be checked for joint separation, soil migration through the joint, cracks greater than 0.01 inches, or settlement and alignment. It also recommends that 100% of all flexible pipes, whether that's HDPE, PVC, CMP, polypropylene, or other flexible pipes, whether they're metal or plastic, should be checked for rips, tears, joint separation, soil migration through the joint, deflection, cracks, localized buckling, bulges, settlement, and alignment. So some people say, well, we'll do CCTV to video the concrete pipe, but we don't need to CCTV the flexible pipe because we'll just pull a mandrel through. But if you notice, the recommendations is if a mandrel isn't going to look for tears or joint separations or any soil migration, it's not going to look at deforming, a weird deforming of the pipe, like with corrugation creep as you compact around the corrugations and they creep into the inside of the pipe. You're not going to notice those things. So it is highly recommended that you video concrete pipe and flexible pipe, whether it's plastic or metal, and do the mandrel test for flexible pipe. No mandrel test necessary for concrete pipe because it doesn't deflect. Post-installation inspection should be performed no sooner than 30 days after completion of installation and final backfill. Again, because we want to make sure that we've got the time for that pipe to stabilize. So you want to do it 30 days after. So after 30 days after you install the pipe. So for concrete pipe, when we look at when we look at concrete pipe, rigid pipe here, we go in with our CCTV. We've got a video that goes through and looks at it. Now with flexible pipe, you can use this laser scanner, this deflectometer that they attach to the video. So you can go through and do both. So you can see what the deflection is, and it shows up on a little graph like this. Now, this is not as common in Utah yet, but if we see more cities and things going to this is a possibility and an option. So it shows what true round looks like in the green circle, and then as you spin this laser around and the deflectometer, it can show you how much the pipe has deflected. And in this case, you can see it's got this pretty severe deflection off to the right-hand side of the screen there, where it's deflecting out of round. So that would exceed your 5% deflection. It would measure it and say, yes, that is unsuitable. That section of pipe needs to be removed and replaced. So those are a couple of different options and some recommendations that we give on what you should be doing with post-installation inspection. So again, as we go back to the scope of this specification, C1479 versus D2321, for concrete pipe, the practice covers the installation of precast concrete pipe intended to be used for conveyances, sewage, industrial waste, and stormwater for construction of culverts. But for flexible pipe, it is recommendations for the installation of buried thermoplastic pipe used in sewers and other gravity flow applications. Recommendations are intended to ensure a stable underground environment for thermoplastic pipe under a wide range of service conditions. However, because of the numerous flexible plastic pipe products available and the inherent variability of natural ground conditions, achieving satisfactory performance of any one product may require modification to provisions contained herein to meet specific project requirements. So again, it's still putting all of that responsibility and that onus on the engineer to make sure that, because things change and things are so different from one project to the next and from one product to the next, it is up to the engineer to determine what they need to do and how this, what they need to include in the plans to ensure that this is installed correctly. So what is an engineer to do? All right. Well, if you're using concrete pipe, an engineered product, you want to make sure that you determine the in-situ soils. You want to select the installation type, type 1, type 2, type 3, or type 4. You then use your fill height tables to determine the strength class required for that size of pipe. You specify the pipe class and the installation type. Then you specify your post-installation requirements. That's it. That's what you do if you're the engineer and you want to use reinforced concrete pipe. Those 5 things that you do. Okay. Now, if you want to use flexible pipe, which is an engineered installation, there are a few more things that you need to do. So first off, you need to determine your in-situ soils. You need to design your flexible pipe based on the in-situ soils or borrowed soils, something that you import or bring in, right? You need to determine the compaction required for structural capacity. You need to calculate your deflection, as we did in our previous webinar. You need to determine bedding requirements based on the field conditions. You need to determine the trench width based on surrounding in-situ soils. You need to verify the depth of cover is acceptable for strength and for flotation. You need to specify the manhole connectors. Make sure you've got the good flexible connectors so that you don't have any issues with the pipe deflects. You want to conduct field monitoring for safety, for installation, for make sure that everything is correct, for trench depth, trench depth, the grade, water conditions, etc. Make sure they're using the correct materials, the density of materials in place, your joints, safety, and last but not least, which is arguably the most critical to make sure that it was installed correctly, you want to specify deflection testing. So if you're using concrete pipe, you look at the 5 things on the side there that you're responsible for that you need to include in the plans. And if you're going to use flexible pipe, you need to look at all these other things that you need to do for your engineered installation. So again, once again, I want to reiterate this and show you again, the engineer, if you're using reinforced concrete pipe, the engineer calls out that it needs to be manufactured per ASTM C76 and installed per ASTM C1479. Manufacturer says, good to go. That's how we manufacture pipe. C76 is met. And installer says, great, C1479, that's the manufacturer's recommendations on installation. Absolutely, we'll install it that way. Everyone is good. Pipe gets installed correctly. For flexible pipe, engineer calls out per manufacturer's recommendations. We go to manufacturer's recommendations, and it says over and over, as per ASTM D2321. And what does D2321 reference? The engineer's responsibility, almost 30 times what your responsibility is as the engineer. So that responsibility comes back to you. So if it fails, if there's an issue with it, sorry, engineers, but it's going to be on you. If you didn't have all of this stuff in the plans to be installed correctly, if you didn't follow every single recommendation, as we pointed out, of what you need to include in the plans there, if you didn't follow all those recommendations and do what the spec told you, it's going to be your responsibility. So if we go back to our hypothetical situation that we posited last webinar and we revisited at the beginning of this one, the construction drawings call for 48 inches of RCP. Okay, the contractor wants to use 48-inch HDPE because his brother-in-law is the plastic pipe sales rep. So contractor plans to install the HDPE just like RCP because he says, well, pipe is pipe and we can install them the same. So you're the project engineer. Do you approve the change as is? I'm hoping that based on the last 2 hours, the webinar from our previous webinar and design, and then this webinar that talked about installation, I'm hoping that you have come to the realization that these pipes are not the same. One is a conduit, one is a conduit and a structure. One is delivered on site as a structure. One, you need to build the structure on site and make sure that it's being done correctly in the field. One is an engineered product, one is an engineered installation. There are so many differences between these two products that we cannot treat them the same. So I'm hoping that you have realized that if you were asked, do you approve the changes, the answer is no. If we look at this, and the last question, and this is the one that really keeps me up at night and worries me and concerns me, is if the HDPE fails because it is substituted for reinforced concrete pipe with no changes to the plans to include specific installation details based on the manufacturer recommended calculations and the recommendations in ASTM D2321, who is liable? So if you swap it out, you didn't change the plans, you didn't update them, you didn't go through D2321 to ensure that you've covered all the bases on how this thing needs to be installed and what's in the plans. If you didn't do all of that and you just allow them to swap out reinforced concrete pipe and install plastic pipe instead of concrete pipe, and you didn't include anything in the plans, who's liable? Who's responsible for that? And the answer is always the engineer, the person that is referenced in the specs, the person who is called out in ASTM D2321 almost 30 times on what their responsibility is. That is the person who is liable. So the key takeaways from this are that rigid and flexible pipe are dramatically different. Flexible pipe cannot be installed the same way as rigid pipe, and the engineer takes on the liability for structural design and the installation of flexible pipe because it is an engineered installation. For more information about this topic or any other topics, feel free to email me at jason.allen@oldcastle.com or visit oldcastleinfrastructure.com.